So guys, in this video we'll look at oil refining and crude oil to start with. Crude oil is a material that is found beneath the earth's crust mostly, or sometimes below oceans and that. And when we drill for it, the crude oil itself is actually a black mixture of substances. It itself is actually very unuseful a lot of the time. Back in history, when it was struck, let's say, over land, it was seen as a negative thing because it was very difficult to deal with and you couldn't build near it or that. So this material, if you like, that comes out of the ground, the crude oil itself is actually pretty useless. And what we're going to look at today is how we make it useful, if you like. But there it is. Like, for leaving cert chemistry, you just have to know that, of course, crude oil comes from the ground essentially. Now it's built up in the ground over a long period of time. It's made from dead plants and animals. That's where the carbon comes from. That's why we're studying it in this area. That's why it's part of carbon chemistry. Crude oil fundamentally is a hydrocarbon. It's made out of hydrogen and carbon, and it also has oxygen and other elements in it as well, as we'll see. We're going to focus mostly on the hydrocarbon part of it though. Oil refining, that's what it looks like when it comes out of the ground. So it's actually like you throw a match in that, it will not light. Now sometimes you see pictures of oil extraction equipment and it's on fire. That's because there's methane gas a lot of the time at the same time above the crude oil well, if you like, underneath the crust of the earth. But essentially, like the black substance itself, the crude oil is very unuseful. It doesn't burn. It does float on water to a certain degree, and it's pretty useless. But how we make it useful then is we take the crude oil and we heat it and we break it up into its fractions. Now that essentially means that we take crude oil and we split it up into individual parts that are more useful. So you have heavy gas oil, lubricating oil, diesel, kerosene, gasoline, naphtha and gas. And this is known as a fractionating column or a distillation column. And what this allows us to do, it allows us to refine the oil. Refine it into different fractions. So the name for these guys are fractions. So this area is not too bad in terms of the chemistry. It's more sort of understanding what these are and how this equipment works. And there's very little to it really. The crude oil is heated, and then much like distillation, but instead of just having water coming off or whatever you're separating in simple distillation using a Liebig condenser, here we have many different things coming off. But just like a Liebig condenser, it is based on boiling point. So the temperature at which it boils off, you see, will give rise to gas. So that's the one that will boil first at a temperature. Then you have naphtha. Naphtha, we'll go through each of these, but naphtha is used as a solvent a lot of the time. You have gasoline. Gasoline is used, now we would call that petrol. So this diagram comes in the States of that, but petroleum effectively is a part of gasoline. Kerosene used to be used as lamps. We'll have a look at that. Outdoor lamps here. Sometimes you can still get kerosene lamps actually. We'll look at that. Diesel is a heavier oil than petrol. Petrol will be back in gasoline. Diesel is a much heavier one. Like if we're talking about number of carbons, the gas here has 1 to 2 carbons in it. Naphtha, you know, we're talking about 3 to 7. Gasoline, you're talking about 5 to 9. Kerosene, you're kind of talking about 8 to 11. And then diesel, you're starting up from 10 to 14. Lubricating oil, that's a thicker oil, if you like. That goes up into the 15 to 22. And then heavy gas oil, you start entering into the mid to late 20s in terms of number of carbons in the molecule, and then you have residual. That would be like bitumen tar and that, so that's above, you're well up into the 30s and 40s there we have, or if not higher. That is the different temperatures. You don't have to worry too much about the temperatures, the actual temperatures at which they boil off, if you like. The most important thing that you remember is that the different fractions, or this fractioning column, is based on boiling point. Each fraction is boiled off has a different boiling point, and therefore gives rise. Now these little things here, these are sieve plates. That's what they're not. That's not a random diagram there. Essentially, when the substance is boiling effectively, it'll push through this sieve plate. If it doesn't boil, it will stay in the layer below. So that's how things make their way up. So every time you go through a sieve plate, it must mean you're still a gas, still a gas, still a gas, still a gas, and still a gas. So that's up. That would make sense. That would be methane and ethane. So they're boiled off. Then you would have gasoline. Gasoline will reach here. It's meant to be in that grey, if you like. It can't go up. It won't go through this sieve plate, if you like. Quite simply because it's not a liquid. It's not a gas anymore. It is in fact a liquid here, and that's how you get that separation. So that's what those little sieve plates are. They allow for ease of separation. But it's just the same as normal distillation. It looks very much more complicated, but the principle is exactly the same. You heat the crude oil, and then it'll go as high as it can as a gas, and then it will either leave as a gas or it'll be liquefied here, liquefied here, liquefied here, liquefied here, based on its boiling point. There's 40 degrees. Petrol is a volatile liquid. It's used in cars. We'll go through these. Refinery gas, that's what you see if you see oil drilling equipment. If you see fire coming out of it, that's the refinery gases burning off. Naphtha is used in chemical production. It's a very useful solvent. Kerosene, along with kerosene lamps and that, it's a heavy fuel. It's used in jet engines as jet fuel. Diesel oil is for heavier cars, like you know, the difference between a diesel engine, you can get diesel engine in cars, but there's no spark plug in them. The compression allows the fuel to ignite. A diesel engine is a much heavier engine, whereas a petrol engine, we'll have a look at that in a second anyway, but a petrol engine effectively ignites the fuel using a spark plug. When it's pumped through I think we've gone through most of that, and essentially there must be monitoring. And this is fractional. Fractions in terms of crude oil are the different parts of crude, the different useful parts that are separated out based on their boiling points. So just remember that gasoline, naphtha, kerosene, gas oil, which is diesel, each of these are considered to be fractions, parts of it. So that's quite important that you'd remember that. And the different hydrocarbons are separated. So a fraction is each one of these useful mixtures that is separated. See, there is mixtures, you know the way I was saying, between C5 and C10. They're not all the same hydrocarbon, but the carbon lengths were roughly the same. So not alone does the boiling point decrease as you go up the oil refinery, so does carbon chain length. Now I hope that makes sense to you, because obviously the two things are linked. Shorter hydrocarbon, less electrons to slosh around, weaker temporary dipoles. Now you need to think about that. Like, they're not independent things. The reason that the boiling point decreases as you go up here is because the molecule is getting shorter. Now we did talk about that as well in another video, but please remember that, because it's like that's one of the fundamental things. I mean, if you have just a few carbons in a chain length, which is fine, you know, the electrons slosh over here, and that gives you a slightly negative end, and that's slightly positive end. Remember, it only lasts for a split second, and then, you know, it would have a neighboring molecule here, and that's this. Then that slightly positive end there would pull over the electrons a little bit, and that would pull over the slightly negative, do that delta negative, delta positive, and you have a sloshing over and back, over and back, over and back. Whereas if you have a big long molecule, you get a much stronger slightly negative, I still call it slightly positive and slightly negative ends, because you have more electrons slosh over and back, over and back. More electrons, bigger slightly positive, slightly negative end. So that's why those two things are linked. They're not obviously independent events. And that's that one. So this is much easier, maybe what we've been doing over the last couple of videos as well. Here to give you some idea what the fraction, you see, and look, it's perfectly linked with the principle of the number of, or the boiling point, of course. Refinery gas, short chains, you see, C1 to C4 I have there. Petrol, C5 to C10, that means that there's 5 carbons, 6 carbons, 7 carbons, 8 carbons, you know, that's a length of carbons, C, 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 you know, in a row, bonded to each other. Naphtha, you see, is around the C7 to C11, I think I said earlier, but in around that. Kerosene is C10 to C14. Oh, see, I was a bit off with the diesel there, 14 to 19 for diesels. The diesel is a bit longer than I said earlier. Lubricating oil then 19 to 35, and fuel oil 30 to 40, and bitumen would have a carbon chain length of greater than 35. To give you some idea, vegetable oil would be around C17, you know. So to give you some idea of the viscousness of the, you know, the more down you go, the more viscous the oil gets, if you like. That means it, you know, it moves more as one. It gets more and more oil-like to the point where it becomes tar, which you know you have to heat it up to get it to move. It doesn't move at room temperature. So bitumen tar is used in roads and that. But yeah, you don't have to worry about the exact numbers for these, but you should know that the carbon chain length increases, and then link that to boiling point. Obviously, as the carbon chain length increases, you will have more sloshing of electrons, a stronger temporary dipole. Yeah, and we said that already, because the larger molecule, higher molecular weight, the more energy. I hope that makes sense to you guys. The longer the molecule, because that's a real connection in the chemistry here. The longer the molecule, the more electrons to slosh over and back, the stronger the temporary dipoles between the molecules. Temporary, remember, is only because the electrons are sloshing around. The different fractions, refinery gas or petroleum gas, that would be the first one. LPG, liquefied petroleum gas. Sometimes you might see that. You should know what LPG stands for, liquefied petroleum gas. That comes up sometimes in Leaving Cert Chemistry. What does the letters LPG stand for in refinery gas? And you would have to say it's liquefied petroleum gas. Now you know that the gas in the laboratory that comes into the laboratory has a smell. Gas doesn't actually have a smell, at least methane doesn't. And what we need to do is add a sulfur containing compound. So that's what this is in the yellow here. That's meant to be a sulfur atom. And they're known as mericaptans. So that smell that when sometimes the ad comes on the TV, if you smell gas, a ringboard gas, and that is to really to link the idea that what you smell is that sulfur containing compound that is mericaptans. So it's not actually the methane itself. The methane itself has no smell. So we add humans add mericaptans to methane so that we can detect leaks. And this is a safety concern. And it's as simple as that. So methane itself actually doesn't have a smell. Or at least not a distinctive smell. So that mericaptans, you would need to know what are mericaptans. They're sulfur containing compounds that are added to gas to give it a smell for safety reasons, because we know then if it's leaking. You can imagine a house filled up with the gas and you could not smell it, how dangerous that would be. And naphtha is a source. Here it is, in this beaker here is shown as a solvent, but it's also used in medicines. Like a huge amount of medicines are made. Organic chemistry, you study organic chemistry, inevitably you'll be studying some sort of medicinal chemistry. a link to that. Plastics like polyethylene is a load of ethene molecules. Poly means many, bonded together. Synthetic fibres used in clothing, detergents, solvents. These are all examples. And naphtha consists of C7 to C10. Kerosene, you might have heard of kerosene lamps. That's what used to be used as street lamps before electricity. This is what a kerosene lamp looks like. A person used to go around every night actually and light the kerosene lamps along the streets. It's also used as some parts of it, at least some lengths of the carbon chains, are used in jet fuel, and paraffin is often used as well. That sentence. Diesel or gas oil. It's more difficult to vaporize than petrol or kerosene, so it's a heavier fuel, so it's used in large machinery like agricultural vehicles or buses. It's used in cars now. That happened. I think that's starting to decrease again, but for a long time there, diesel cars were sort of being promoted as a useful alternative to petrol engines, producing nitric oxides or less nitric oxides. But the problem is they do produce particulates, and particulates are a major issue in that particulates have they're damaging to lungs, and they cause smog and nitrogen oxides. So diesel, even though it was seen, they're talking about increasing the tax on diesel cars now for that reason. It's not a clean fuel now. It's a heavy fuel. It doesn't produce the nitrogen oxides to the same extent, but it does produce particulates which are quite harmful. Lubricating oil then from C19 to C35 has a high boiling range. It's not suitable as a fuel as it cannot be vaporized easily, but it's used to make sure that the pistons and all the different crankshaft and the different things that operate in the car, that they do not wear as fast as maybe they would. So it has a role in that. Wear would obviously mean then it would lead to breakages in engines. Fuel oil is it's not used as in the same sense that petrol or diesel. Petrol and diesel are vaporized, so it's put in as molecules. Fuel oil is sprayed in, almost like spray coming out of a detergent spray can, or Dettol or one of the. It's fine droplets that's sprayed onto an ignition source. So you can imagine it's not like setting a light to a gas. These are tiny droplets. Now they are tiny, but they are definitely droplets. They're not molecules. So the explosion creates an awful lot of vibration, because it's not like lighting a gas that you would with petrol or diesel or indeed methane in the laboratory. So this is an example. They're used in very large ships. It's used because it's a great source of fuel, but you couldn't use it in a smaller vehicle because quite simply the vibrations produced by it would just be too much. It's also used in power stations and heating plants as well. Bitumen tar is an example of that's when you go up above 35 carbons. You've got so strong temporary boiling or temporary dipoles now that it actually can hold as a solid. So even though it's a non-polar molecule, it's holding as a solid at room temperature, and the boiling all the way up to 500 degrees Celsius. So it's too high to be used as a fuel because it's not vaporized, it's not turned into a vapor easily, but it is very, very useful in terms of road. It's used as a road covering or that. It's also used in roofing as well, and in waterproofing swimming pools and that, and waterproofing roofs. And the next little thing we'll look at is the principle of knocking. So knocking is a term that is used for the autoignition of a fuel within a piston. And what I'll do is I'll show you what a piston is first, and then perhaps we can then look at the principle of knocking. This is essentially inside the car engine. If you look at this, now you only have to know this just so you know what knocking is, so don't get too worried about the exact details of this thing. But this is a piston, and this is what eventually would cause the car wheel to turn, indeed the engine to turn. So essentially what happens here in a 4-stroke engine, or in any piston anyway, there's an inlet valve. So from the carburetor, the air-petrol mixture is brought into this chamber which is known as a piston. Well, a cylinder, but the piston is within it. And when the air fuel mixture comes in, it's drawn in as this goes down. So that's almost like a syringe. You know, as that goes down, it will draw in the fuel petrol mixture. So now the piston, you see it's off center, it's not in the center, so it's off the center of this wheel. So the wheel will go around, and as it goes around, then it'll start going back up again. Now at that point, this will close. So the fuel is drawn in, this goes all the way to the bottom, it comes back around, and it's starting to push the piston back up again. This will close. And what happens then, as the piston goes up, the air-fuel mixture is compressed to such a point where it reaches the top, and this spark plug will ignite the compressed fuel oil mixture. Now you can imagine, number one, you're igniting the fuel-air mixture, the petrol-air mixture, but number two, it's compressed at this point. So the molecules are all really close together. So the explosion, the ensuing explosion, causes the piston to be forced downwards rapidly, turning this wheel once again, you see. And as it turns the wheel, you're talking about it turning the wheels of the car eventually outside, you see. And as that explosion forces the piston down, this wheel will shut around. As you see, it's off center like the old railway. The way that if you saw that before, but in any case, it's off center. I guess you'd get the idea of that if that's forced down, it'll go around, and then as it goes back up again, now this valve will open, because remember the explosion just happened. The piston was forced downwards, the wheel went around, but now it will come back up again inevitably, and when it comes back up again, this exhaust valve opens, and all that burnt fuel and gases that's left over. Now there's some nitrogen oxides there because that's in air, and because of the high temperature produced by the spark plug, there's some nitrogen oxides. There'll be inevitably some carbon monoxide because there probably wasn't sufficient, or most likely there wasn't sufficient oxygen to make carbon dioxide in a piston in a car engine. And you also will have some unburnt hydrocarbons. Now hopefully very little of that, but inevitably you'll have some. And that's all the exhaust, and that goes out. On the return back up, you see, that's known as the exhaust stroke. The stroke being this thing going up and down, up and down. And that then, guys, brings you to the end of the cycle, and it goes back to the start again where it draws in the new fuel mixture. So you see the new fuel mixture comes in, the piston draws it in as it goes down, the piston comes back up, compresses the fuel, the spark plug ignites it, this explosion forces the piston back down again, turning the wheel, and when it comes back up again, this exhaust valve will open and all the waste will be forced out. And then it will come back down and draw in, come back up again and draw in new fuel in the next cycle. So you see there's more than one up and down in one cycle. It draws in the fuel, comes back up, compresses the fuel, explosion, the spark plug will go down, or the piston will go down, my apologies, after the spark plug opens it or lights it. It will come around, it'll go back up again, and all this exhaust valve will open. And the timing of an engine, which is really important, is how these valves work together and indeed work between 4 pistons, as would be the case in a 4-stroke engine. However, that would be here you have it again. You see the mixture ignites again when the spark is filled. Now the difference is when you have, that would be normal, you see. So that's the reason I had to tell you all about this. Really it's for this point, that when you have normal ignition of the fuel will ignite when the piston is at the top. Do you remember I said that earlier? That it comes all the way to the top, compresses the fuel, the piston will ignite it. And then that'll force the piston down and you have the turning of the engine. And that's off to the exhaust there as before, and that's in from the fuel tank. Or the carburetor really. But you see what happens here on the left hand side. It has ignited before the piston has reached the top. And that's what's known as knocking. It's as simple as that. It's an auto ignition or ignition before the fuel should ignite or when we would want it to ignite. And that's knocking, guys. Now the reason it's called knocking or pinging is it actually creates that sound. So auto ignition is the early explosion. So instead of it igniting here with the spark plug when we want it to, it ignites on as the piston is the way up, and you can imagine the shudder that creates. As the piston is on the way up, the fuel ignites. So you imagine this is going against itself, if you like. And there's, you know, in a car engine you're going to have 4 other pistons pushing that up, so it creates an awful vibration and pinging sound. And how we do it has actually got to do with the fuel, which is interesting. It's not an engine problem, it's a fuel problem. So straight chain alkanes tend to cause knocking. So that's why we try and make branched ones. You remember isomers? So these are isomers, you see. Remember, they're the same molecular formula but different structural formula. Like if you count up all the carbons and hydrogens here, it's the same number here as here. However, this would have a better ability to resist that auto ignition that we were just talking about, that knocking problem. So don't worry, like when I went through the detail of this car engine, I probably would have got a bit carried away with it. Really, for you guys, you just need to know this principle, but it'd be hard for me to explain this unless I did in fact go through the other part first. So instead of the fuel igniting when the piston goes to the top, it ignites early, if you like. And that's what's known as auto ignition. Now we will look at octane number in the next video.